All right, well, welcome everyone to the September 18th SIG Node meeting. I have two items on today's agenda. Actually, if we can invert the order, that would be fine with me. So Connor or Bala or Luis, do you want to talk through your NUMA manager proposal and demo? I see Connor. Hopefully Connor can talk.
Yeah, I can. I think Louise is ready to present, so maybe we just give her a second to fix her mic.
Okay, yeah, no problem. Okay, is that LM Daly? I might have missed that earlier. Sorry.
Yeah, that's Louise.
But I guess what Luis is getting ready, we have to get the release notes out for 112. I took a stab at writing them this morning for SIG Node. Do not believe I missed anything, but basically discussed that the pod share process namespace feature graduated from alpha to beta. The runtime class alpha feature was introduced to support multiple runtime options per node. The custom CFS quota period was introduced as an alpha feature to allow you to change the CFS quota period on the node, which helped those who had complained about latency sensitive workloads that still wanted to use quota. And then aside from that, it seems like we mostly just pushed through a number of bug fixes and started iterating more designed for future features. But I just want to make sure from the group here that I did not miss any particular item that they wanted to call out in the release notes, but from my perspective, that seemed to be the three major things that we did this release. So folks do have other things they want to call out, please reach out to me or Dawn. I think we're trying to get the release notes done by Thursday. So with that, Luis, are you ready to present?
Can anyone hear me now?
Yep.
Oh, okay, great. Okay. Yeah, I'll present my screen now. Sorry about that. So I was just going to do a quick run through of the proposal in case anyone on the call isn't aware of it. And then I'll dive into the demo we have of the implementation that's in the proposal. So if I skip anything that anyone is not aware of, or if I am going through something that everyone already knows, then just tell me to skip on. So the main part of the proposal I want to go through is just the actual interface and the flow of the demo that I'll show. So we created the proposal back in January, I think, and it hasn't changed too much, and the demo very much follows what's in the proposal. So we have a NUMA manager component that's now within kubelet, actually within the container manager with CPU manager and device manager, so within the same directory hierarchy. So the manager itself is a pod admit handler, so it's consulted every time a pod comes into kubelet. It contains a store. This is where NUMA hint providers can query NUMA Manager to get back affinity for a particular pod and container. We then have a list of hint providers, which are the components that tell NUMA Manager where to align resources, and NUMA Manager can use what they send back to create an alignment for a pod and container. And then there's just a remove pod to obviously remove a pod from the store. So we have a bit mask for storing the NUMA alignment. So if I go down here, it's easier to show. So a bit mask for a dual socket system could look something like this. So 01 would donate that CPU manager can satisfy the request on socket 1. It can satisfy the request on socket 0, and it can satisfy the request across sockets. So that's what the NUMA mask structure is. And then, as I said, store is for the hint providers that can query NUMA Manager when they're actually making the assignments, and return the NUMA mask for the particular pod container that they're querying about. And then the hint provider is the interface that any components that care about NUMA must implement. So they take in a pod container and return a mask of like below, and a Boolean as to whether there is alignment or not. So this is kind of the overall diagram of the implementation. So we have two hint providers at the moment, CPU manager and device manager. So they both implement that get NUMA hints method. And then NUMA manager will be called when the emit handlers are called. It'll ask each of the hint providers to provide back the affinity for that particular container. And then NUMA manager will do bitwise AND of the masks that are returned and store the first positive result. So as you can see in this scenario, we did 0, 1, 1, 0, 1, 1, and 1, 0. So NUMA manager would have bitwise and 0, 1, 1, 0, 1, 1. So 1, 0 was the first positive result, so it would have stored that. So just a quick overview of the flow. So this is when NUMA manager is called, or when NUMA manager is added as a hint, an admit handler. So during kublet's initialization, it stores a bunch of emit handlers, and so NUMA manager is added as one of those there. And then for the actual creation of NUMA manager and the addition of hint providers, when the container manager is created, NUMA manager is also created. And then when container manager creates the hint providers, so in this case, device manager and CPU manager, it adds those as hint providers to NUMA manager. So NUMA manager knows who to contact when a pod comes in and asks for NUMA alignment. And then this is when the actual alignment of the pod is done. So when can emit pod is called, NUMA manager, which is an emit handler, is called. It calls get NUMA hints function of each of the hint providers it's aware of, and they send back the mask, and it can then store the result. So that's pretty much the flow. And then when the hint providers actually make the allocation decisions, they query back to NUMA manager to ask what is the best alignment for this container. And as their hints, the components can decide really what to do with that information. So that's pretty much what I'll show in the demo. Is there any questions before I go into the demo? If not, I just want to show first, this is the node I'm running on, just so the architecture is, yeah.
I just wanted to add one kind of background note related to kind of the history behind this. This was kind of a feature that was, or not a feature, but a behavior that was punted on kind of at the beginning of, or I guess the end of last year, because the CPU manager and the device manager were still, basically they were designed and implemented in parallel. And so this kind of next step of making them coherent was always kind of understood as something that needed to happen, but that couldn't happen, or that would make the implementation extremely kind of like too high coupled as they were both in their alpha phases. So just a historical note.
Okay, thanks, Connor. So yes, this is the architecture of the system that I am running the demo on, so it just makes it easier to visualize what's going on. So I have a dual socket system, it's hyperthread enabled. So I have 0 to 21, 44 to 65 on socket 0 for CPUs, their core and hyperthread. And then I have 22 to 43 and 66 to 87 on socket 1. I've created 2 dummy device plugins. So I have the orange is device plugin 1 and the purple is device plugin 2. So they basically just send back arbitrary values for device plugins just to show how NUMA manager can align devices. So to do that, we're proposing an addition to the device plugin API. So the device plugins can send back socket information in some form so that the device manager can store that and use it to create the NUMA hints. So what I've done in the demo is I have actually added a socket field to the device plugin API. But that's a demo can be changed there, but I send back an integer value for socket along with the device ID and the health. So the in this scenario, device 251 would send back socket 0 with the ID and its health. And that's just the overall system that this demo is running on. So if we go here, hopefully that is big enough writing. So I've actually have the 2 device plugins running, so test device plugin 1 and test device plugin 2. I can show you the logs for each, so it'll just show the devices they have sent back. So here we can see, so this is 251, 261, and 271. As in the diagram, so 251 is on socket 0, 261 and 271 are on socket 1. And that's how I've updated the profile for device plugins, so I've added this additional field. And then I have the second device plugin, so that's 351, 361, and 371, and we've 2 on socket 0 and 1 on socket 1. So what I'm going to do next is I have some pods. So this first pod, so what I've done in this demo is that to kind of correlate with how CPU Manager works, NUMA Manager will only align guaranteed pods because CPU Manager will only align guaranteed pods that are making integral CPU requests. So in order to get the alignment, obviously we need to use guaranteed pods. So if it's best effort or burstable, basically the admit handler for NUMA Manager will be called and it'll just return true and the pod will be admitted as normal. And if it's guaranteed pod, NUMA Manager will go and try and align the resources.
Can I ask a quick question? So if the guaranteed pod is unable to have its resources aligned, is it a policy choice to reject that pod entirely in admission?
Yeah, so we have planned for possibly 2 policies, strict and preferred. So in this demo, I actually have preferred on, so it will still admit the pod and give you the resources across sockets if it can't align them, but it will try. And then the strict one, which I also did an implementation of, it fails the pod and it returns a NUMA affinity error. So it's kind of, it would be probably a kubelet flag to decide whether you want strict or preferred on.
Very cool, thank you.
So I'll just run this pod and I'll just show that it basically aligns these. So this is 4 CPUs, so that'll be 2 physical, 4 hyperthreads, and a device each. So what I did in the device plugin, just to easily show what devices are allocated, I just populated an environment variable with the ID and the socket that was given to the container. So if we just go into the pod, we'll be able to see what devices it got and what cores it got. So in here, so we got 271 and 371, which are both on socket 1. So it aligned those devices, and then if I check proc self status, I'll see what cores I was given. So I was given 22 and 23 and 66 and 67. So they should also be on socket 1. So if we go 66 and 67, and they're hyperthread siblings, so they're both on socket 1. So it aligned all those resources together. And then just to show that it will still admit the pod and still run, but it will basically not align the resources if it can't. I have another pod, which is a no affinity pod. So if we go back to the diagram, we got aligned on socket 1. So we got this test, one of these test devices, and one of these tests, this device and this device. So if I ask for now 2, if I ask for 1 here and 2 here, it'll only be able to give me test devices across sockets. So let me just change these. And and I'll just show the same thing. So, oh no, it's actually able to give me the 3 on socket 0. So I obviously had 2 left on socket 0 for the second device plugin. So it did work in this case. So I got the same as well. I got the 3 devices aligned, and I got the cores aligned as well. But in the case that it couldn't do it, it would still run. It would just give me the device across sockets in this preferred policy. And that's pretty much the extent of the demo. If there's any questions, please shout.
Hi, this is Jiaying. I have some quick questions. So first, you mentioned the policy can be best effort or required. Is it like a NUMA manager policy setting expressed through kubelet flags, or is something a pod can specify?
It would be a kubelet flag similar to the CPU manager static and none policy. So we're thinking a stricter preferred policy as a flag as well. Yeah.
Okay, so it's probably like people, if people want required policy, they will create some special node group with that setting for a bunch of nodes.
Yeah, we assume high priority workloads or workloads that require it will use the stricter required policy. Yeah.
And for required, in that case, kubelet will just fill the emission of the pod, yeah, if it doesn't have the required resource.
Yeah, exactly.
Okay. Another question. So for the resource name, I noticed that you actually put some special string in the resource name. But do you expect to still use the standard like a resource name? Like typically we expect the resource name is just something vendor specified. So for example, for GPU, for NVIDIA GPU is nvidia.com/GPU, but that resource can be exported on a node that may support NUMA or may not support NUMA, but it's the same resource name. Do you still expect that to be true?
I think maybe I'm not following. So,
I think I get what she's asking. But,
okay.
I think the assumption is, wouldn't we taint the node with the corresponding policy? Then your pod would have to explicitly tolerate that node that said, I provide the higher guarantee, or direct your node to it. Like, I think the labels, the resource name being the same is fine. I mean, and you can quote it separately with Vish's latest proposal.
I think that's right. And then the second part to it is probably, you know, it's up to your device plugin to pass back, you know, socket preferences for the device. If you don't care, just pass back a full mask.
Okay, but like for some old version device plugin, that information may not be populated.
Yeah. So it'll be an optional field in the protobus. If you don't supply it, we just assume that you don't support any sort of NUMA affinity preference.
So we expect some like cluster API part is responsible for either labeling those nodes supporting NUMA or like adding special taints on those nodes to differentiate whether the nodes support NUMA or not.
I'm not sure. I mean, that's not part of the proposal. I guess you could make the same argument for like the static CPU manager. Right now, we don't export any labels or taints or anything like that when you change the CPU manager policy. As an operator, you might want that, but it's kind of, I think, out of the scope that we considered for this part.
Okay.
Have you done any investigation or thought on how we could extend the work you have here to demonstrate locality of huge pages?
I originally, way back in December, created a different POC for Numa, and I did include huge pages there. One of the I ran into that C Advisor advertises them entirely for a node as opposed to per socket, so a change is required there. And then there was, with device and CPU manager, there is managers, so there is a known place to contact. I guess there isn't the same for huge pages, but I was able in that original POC to align them, but it was a couple more steps.
Okay. Do you have those details written up in your CAP? I mean, I think I wrote the C Advisor huge page stuff, so I'd be happy to extend it. And so,
yeah, I think we had huge pages as for beta, so we didn't really go too in depth in the CAP for huge pages.
Okay.
So question. So what kind of workloads you think will benefit most from this feature, and in what environment?
Yeah, for sure. We have one use case is DPDK workloads. So if they're using an SRIV capable NIC, they'll most likely be using the SRIV device plugin, and then they need pinned cores. So they'll definitely benefit from Numa Manager aligning the cores with the SRIV NIC. Or basically anything that requires device locality with the CPU will benefit from that, but that's a major one we have.
Mm-hmm. So for that environment, I guess typical settings for a node, most pods running there will be guaranteed pods and high performance, requiring high performance. You don't really expect such a pod to share the same node with, say, for example, best effort pod.
I'm not too sure whether it would be.
I think, Gian, I think you would. Just other pods that are maybe not best effort, but definitely probably burstable, that are providing cluster services themselves, so that your SDN would probably still be on that running as a pod. Your monitoring component would still probably be there running as a pod. So I would still think you'd have other components running on that kubelet that are not guaranteed.
We've seen use cases where, for example, you may have a packet forwarding application where you have multiple containers in the pod, where one is the guaranteed latency sensitive one that you want max performance out of, but you may bundle the control plane as a separate container in the same pod, so that you have shared fate, shared scheduling, but different kind of resource handling on the node.
But I think the guaranteed QoS is a pod level thing. So if you want to group them into a single pod, every container need to have limit and request set the equal, right?
That's true. So these decisions, if it wasn't clear, are container level, same as the device allocations, and also the CPU affinity decisions that the CPU manager made.
It's basically integral cores in a pod that's in a guaranteed quas class. So if your container can still be in a guaranteed quas class and not make integral core requests. Your pod can be, or you could have multiple containers in a pod where one makes a fractional request and the other one makes an integral one. And I believe, Connor, the integral would still have gotten the CPU manager to get picked up, and it can still be in the guaranteed quas tier when you send those CPU requests.
Yeah, Levente here. I just wanted to second what Connor was saying. So coming from Nokia, and we are kind of doing these applications, and this is exactly how they are built up. So especially if you are going to the microservices architecture way, there are certain components which do require these let's say specializations, and these are basically the DPDK using data plane workloads, but the same application has also a lot of OEM functionality related to, I don't know, handling logging, integrating to EMS system, pushing alarms and performance counters. So usually those kind of parts of the application are pretty happy with whatever shared CPU sets they are getting, but they are still part of the same application.
If I understand the comments correctly, you intend to just look at the container level request and image setting instead of like across the whole pod? Is it what you are suggesting?
Yeah, so when the pod comes in, we just check the quaz class, and then per container, we align the resources.
Right.
Okay.
So that's why I was saying you can be in the guaranteed quaz class and have a pod whose total CPU request and limit was like 1.5 cores. But of that, one of those containers was making an integral core request. And then the CPU alignment will be guaranteed for that container.
Okay.
That made the integral request within that overall pod.
Okay.
So I don't know if there are other questions. I will say I very impressive demo in POC, and it helps us review the CAP more closely. Is there a place that you can make this branch visible for folks who want to look at the code a little bit more?
Yeah, oh, I never added that to the, yeah, I have a branch. I'll add it to the agenda.
Okay. And then as we look to Cube 113 planning, I think we had been trying to decide like what would be the right incremental thing to tackle next, where we haven't done much in the space during 112 per se, but this to me looks like a good candidate for us looking to tackle in 113. So I very much appreciate you sharing the POC and the work from Intel.
Thank you. And thanks for the feedback, everyone. It's great. And it would be really great if we could get this on the roadmap for 113. And I'm definitely committed to, I can do development for it, for sure.
Okay.
There's a related CAP, number 2435, which is make the kubelet CPU manager respect ISO CPUs. When we have NUMA alignment, this is a natural next step to tee up for like cleaning up the cores and making the whole thing production ready.
Is it something you'd like to tackle in parallel, Jeremy, or you're saying like 114 that might be a priority?
I mean, I would.
Possible.
So here's the thing. Without that, we can't actually really turn this on in prod. Even the NUMA manager, like it will have certain use cases for I/O, particularly like InfiniBand related I/O, and some network I/O for SRILV, of course. I would ask Leventi the same question. Would you turn on the NUMA manager without the ability to partition the system, as you're probably doing now?
Definitely we will turn it on, but I have to say that our infrastructure on which I will turn it on, probably will separate still these workloads on the node level because of this, what just mentioned. B, probably my infrastructure will have still some kind of proprietary, let's say, hacks, which will do some CPU pool partitioning outside of Kubernetes. So yes and no, the answer to the same question.
I mean,
So,
that's,
yeah,
that's a valid answer. To me, what
I run a vanilla Kubernetes, yeah, definitely, probably not.
So we haven't really done a deep dive, I feel like, on the ISO CPU discussion in a while, and I'm not even sure as I think through this if we treated system reserved or cube reserved as a guaranteed quads entity itself, and then set enforce node allocatable to more than just pods, but set it to system or cube reserved as well. In theory, Jeremy, couldn't the kubelet just set the CPU isolation appropriately for that entire C group subhierarchy without issue? Like, would you even need ISO CPU?
We don't necessarily need ISO CPUs. We also have a systemd implementation that works well. I can't say anyone's ever tested what you just described, so I would just say that a ton of work went into validating the two settings that we support right now, that Red Hat supports. We would have to just validate like a prototype.
Yeah, but just in theory to me, like the system C group or the cube reserve C group is just another pod bounding box, you know, just or similar to any other bounding box. And I think it's worth talking through or seeing through if that broke down anywhere, just so that people don't have to manage things outside of the kubelet.
Even in my cap, I just would like to point out that I also didn't like really focused on ISO CPUs. I just brought it up as like an example for an already existing parameter which kind of serves this purpose. But I think the important thing is that we need a parameter with which we can set like these thresholds explicitly instead of just trying to figure it out. And always assume that these cube reserved and system reserved, let's say, resources, specifically when it comes to the CPU, are always coming like from the low numbered CPUs. So I think that's what's hurting. But I think like everyone is very open to have any kind of like optionality or control this functionality in any way, myself included, even though I really titled the cap like respecting ISO CPUs. I think the important thing is like to have the functionality. Like how to control it is like secondary concern and kind of like a lower level implementation detail even for me.
So Derek, are you suggesting like making system reserved more like an explicit CPU list?
I'm saying probably on, I don't know how many cube hosts even actually put the kubelet in a separate C group hierarchy, say from system slice when you're running on a systemd host. So I think probably 99.99999% of the Kubernetes hosts in the world are running kubelet underneath system slice. And so if you treated system reserve, which mapped to system slice on that topology as a integral CPU request and made the kubelet on startup assign everything under system slice CPU in the same way we would have done for any other container that was emitted, that the kubelet could take ownership of the problem entirely and we wouldn't have to do any configuration to the host prior to just starting the kubelet. And that's don't know where that breaks down, but that seems to me like
it breaks down on kernel threads, I'm pretty sure. That's part of the problem. But let's definitely test it because it might get us a big win. I agree in terms of like the implementation details are not really important. But in the past, the kernel threads were the problem for user space tuning.
Yeah, I guess, yeah, I don't like to design right now. And so I all I'm saying is I prefer if we do solutions that don't require you to do much host configuration, have the kubelet just do the right thing. So for the sake of following discussions, I guess, Luis, I think we should get your CAP reviewed and when Don and I go through the 113 planning, this seems like a good candidate, and appreciate everyone's help. And if there's other topics or discussions that we want to bring up today, let's talk about them now. Otherwise, we can meet again next week, and I'll upload the recording for those who want to see the demo again when Zoom converts it this afternoon.
This is Robert Krawitz. Just real quick, I updated the ephemeral storage quota PR and the accompanying cap. So if anybody else wants to look at it. I also appreciate having the code looked at also. I'm not going to be here from Thursday through the following Friday and then returning the beginning of October. So don't expect any response after tomorrow. That's it.
Okay, thanks, Robert. I know that's another feature that we were talking about pulling to 113 as well. So if there's nothing else, we will sync up again next week. And big thank you to Intel for dumbing today. Bye, everyone.
Thanks, everyone. Bye-bye.
Bye.